In section 4.3, we're going to look at logarithmic functions. In particular, we're going to convert between the exponential form and the logarithmic form. We'll evaluate logarithmic expressions, apply basic properties of logarithms, graph the logarithm, and see some applications involving logarithmic functions. Example 1 is a motivating example. Solve for x. 2 raised to the x power is equal to 8. So if you had 2, what power would you raise that to in order to get 8? Well, the answer is 3. And you would say, in this case, x is equal to 3. If you can do that, you can do logarithms. A logarithm is simply the exponent that comes out of an equation like this. Here's the definition. If x and b are positive, real numbers, such that b is not equal to 1, then y equals log base b of x is the logarithmic function in base b. Now there is a conversion equation that goes from exponentials into logs. You have b raised to the m power is equal to x, and that can be converted into a log form, that is log base b of x equals m. So notice that m is the answer of a log, and from the exponential part, that was the exponent. So logs are nothing more than exponents. There's some terminology here. The base b is called the base. The x is called the argument. Example 2. Convert 7 squared equals 49 to a logarithmic form. So here we would write log. So whatever the base of the exponential is the base of the log, so it's base 7. The argument is what would be the answer from the exponential form. So you're going to take the argument to be 49. So this says log base 7 of 49. Log base 7 of 49 is equal to the exponent that you would raise 7 to in order to get 49. And of course that's 2, as given in the problem. Example 3. Convert 4 raised to the p power equal to q to a logarithmic form. So again, have log, the base is 4. The answer from the exponent form was q, so that's the argument in the log, and that's equal to the exponent p. Example 4. Convert log base 9 of 3 equals 1/2 to exponential form. So the base is 9. The answer to a log is the exponent, so the answer here is 1/2. So the exponent becomes 1/2. And then the answer is the argument from the log. So 9 to the 1/2 power equals 3. Example 5. Convert log base c of 8 equals 2r to an exponential form. So we have base c. The exponent is what is equal to the log, so that's 2r, all of that. And that's equal to 8. Let's look at page 2. Example 6. Evaluate each logarithm. So log base 2 of 16. So the question you're really trying to answer here is 2 raised to what power is equal to 16? And you could count it up, or maybe you know this one. The answer is 4. 2 times 2 times 2 times 2 is 16. So log base 2 of 16 is 4. Next, log base 12 of 12. So 12 raised to what power is 12? Well, that answer is 1. Next, log base 5 of 1. So 5 raised to what power is equal to 1? The answer is 0. In fact, for any positive number, a to the 0 power is equal to 1. Part D, log base 1/2 of 4 is equal to what? So this one would be 1/2 raised to what power is equal to 4? And there's two parts to this one. First off, you're going from a 2 to a 4, so that involves squaring. But also you're going from the reciprocal form, 1/2, to the non-reciprocal form of a 4. So that involves a negative. Remember this rule. A to the negative 1 is equal to 1 over a. And that works backwards as well. 1 over a to the negative 1 is equal to a. So the answer here is negative 2. Lastly, E, log base 5 of 1/25. So 5 raised to what power is equal to 1 over 25? Well, it's the same thing. To go from 5 to 25, you need to square it. And to go from non-reciprocal to reciprocal form, you need a negative. So the answer is negative 2. Next, let's look at some very special logarithmic functions. These are called the common log and the natural log. The common log is denoted by just log. Notice that there is no base. Nothing is written there. When there is nothing written there, it is assumed that the base is base 10, and it is called the common log. They use this a lot in scientific notation, where things are times 10 to some power and such. So that's the common log. Next is the natural log. The symbol for natural log is ln of x. There's nothing written here, but it's also not just log, it's ln. So when you have ln, the base is understood to be e, the natural base, the number that we talked about in the last lesson. Example 7. Evaluate each logarithm. A. Common log of 100. So the question here is 10 to what power is equal to 100? And of course the answer is 2. So the log of 100 is 2. Part B, what is the natural log of e to the 5th? So the base of the natural log is e. You need to know what power is going to make e be equal to e to the 5th. Well, there it is. It's just sitting there. It's a 5. So the natural log of e to the 5th is 5. We study these logs, the common log and the natural log, because primarily these are the two log functions that you have on your calculator. Let's take a look at example 8. Use a calculator to evaluate each of the following. Common log of 31,589. If you type that in the calculator, you get 4.4995. Part B, natural log of 1.214. If you type that in, you get 0.1939. C, log in base 5 of 12.8. This one you may or may not be able to do. Some calculators have a function called log base. Log base takes two arguments, and you separate them by a comma. So when you are doing the x and the b, that's the same thing as log base b of x. So notice that the base goes on the right side. To compute log base 5 of 12.8 in your calculator, you would have log base of 12.8 comma 5. And this works out to be 1.5841. If you don't have this special function, you'll have to do it using the base changing formula, which is coming up in a later lesson. Let's look at the properties of logarithms. So number 1 is log base b of 1 is equal to 0. Now you should be able to justify each of these properties by thinking back to the exponential property that it comes from. If we have log base b of 1, If we have log base b of 1 is equal to 0, then that comes from b raised to the 0 power is equal to 1. Two, log base b of b is equal to 1. That comes from the exponential b raised to the first power is equal to b. Three and four is a little bit complicated. What we have to understand now is that I can set up functions for the exponential and for the logarithm. So let's let f of x be the exponential function b to the x. The inverse function for the exponential function is the log function. That is the relationship. And that's why we reordered some of the curriculum whenever we taught this. We just learned about inverse functions, and this is where we need them, so that we can establish the relationship between the exponential and the log. They are inverses of each other. One of the concepts that we learned when we studied inverse functions was this fundamental identity. If you take the inverse of a function, f, and you compose it with f itself, then that has to be equal to x. Similarly, I need to be able to do this the other way as well. So f composed with f inverse of x is equal to x as well. That is the fundamental identity from inverses. Now, what does that look like when the function is the exponential function and the log function? Well, if we do this first one, f inverse of f of x the inverse function is the log function, so that would be log base b, and then we need to evaluate that at f of x, which is the exponential function, b to the x, but by the rule directly above it, we know that that has to be equal to x. And that is property 3. So when you take the log in base b of b to the x, that is equal to x. The other property, f composed with f inverse. The f function is b raised to a power. Okay, put your cell phones away. B raised to the f inverse. The inverse function is the log function, so it's log base b of x by the inverse rule. That has to be equal to x as well. So we get x there. So property 3 is log base b of b to the x is x. Property 4 is b raised to the log base b of x is equal to x. My favorite one here is number 4 because it's the one that makes the most sense. I told you from the very beginning that logarithms represent exponents. Where is the logarithm in property 4? It's in the exponent. Log base b of x is the particular exponent that you would raise b to in order to get x, and that's exactly what's going on in property 4. Let's use these properties and solve problems in example 9. A, log base 9 of 1. So the log in any base of 1 is always equal to 0. That's property number 1. B, log base 11 of 11. That's equal to 1. That's property number 2. C, log base 7 of 7 raised to the square root of x. That is property 3, so that answer is just square root of x. And then D, 4 raised to the log base 4 of 5. That is 5. That's log property number 4. The D one says 4 raised to the exponent that I should raise 4 to in order to get a 5 is equal to 5. That's exactly what that says. All right, let's look at the graphs of logarithm functions. So first we start with the functions y is equal to b to the x and y equal to log base b of x are inverse functions. Let's look at the graph. We want to graph the graph of log base 2 of x. We want to put that on the same graph as y is equal to 2 to the x. Since they are inverse functions, what property do they have graphically? They are reflections over the line y equals x. So there's the line y equals x. And now all I have to do is take each point on 2 to the x and switch it around. I'll start with the easier ones here. So this is the point 0, 1. That means on the inverse function, on the log function, that's going to switch over to 1, 0. Another point is 1, 2. And that switches over to 2, 1. Another point would be 2, 4. And that's going to switch over to 4, 2. One more point on the right side here. This is 3, 8, which changes over to 8, 3. Let's do a few points on the negative side. When x is equal to -1, we get 1/2. That's because 2 to the -1 power is 1/2. To mark that, we'll go to where x is equal to 1/2 and go down to -1. So that point there is 1/2, -1. Let's do one more here. That there's the point -2, 1/4, which means we're going to get the point when x is 1/4, y is negative. When x is 1/4, y is -2. So we should be able to connect these dots in the reflection over the line y equals x. Does it ever hit or cross the y-axis? No. That's because the original graph, y equals 2 to the x, never hits or crosses the x-axis. And since you're doing an inverse, you just switch them around. So let's write up some notes here. Since y equals 2 to the x, and y equals log base 2 of x are inverse functions, the points x, y on y equals 2 to the x are reversed to y, x on y equals log base 2 of x. And then let's just make a little chart here. We have y is equal to 2 to the x on the left, and y is equal to log base 2 of x on the right. Now recall from the section on exponentials, the domain of the exponential is -infinity to infinity. If I switch that over to the inverse, that becomes the range. So the range of log base 2 of x is negative infinity to infinity. The range of the exponential was 0 to infinity. You can see that here in the red graph. It's always above the x-axis. When you take the inverse function, you switch the range over to the domain. So the domain of the log function is 0 to infinity. Finally, the exponential has a horizontal asymptote at y equals 0. When you switch that over to the inverse, what do you get? Get a vertical asymptote of x equals 0. Again, you're just switching out the x's and the y's. Let's take a look at page 4 and the graphs of logarithmic functions. So f of x is equal to log base b of x. That graph has the following properties. The domain is 0 to infinity. The range is negative infinity to infinity. There's a vertical asymptote at x equals 0. It passes through the points 1, 0 and b, 1. And the easiest way to remember that is because when we graph the exponential, we went through the point 0, 1 and 1, b. Now we're doing the inverse, so it's the opposite points. And then we have a similar statement about the increasing or decreasing nature of the logarithmic graph. If the base is greater than 1, then it's increasing. If the base is between 0 and 1, then it is decreasing. Let's graph what those actually look like here on the side. We have two different graphs. If the b is greater than 1, then that's the increasing graph. And it looks like the following. We have a vertical asymptote at x equals 0. We have a domain that starts at 0, doesn't include 0, but starts at 0, and then the increasing one rises as it goes to the right. It passes through the points 1, 0 and b, 1. For b that is between 0 and 1, that is the decreasing graph. And it looks like the following. It still has a vertical asymptote at x equals 0, but it goes to positive infinity from the right side. It still goes through the point 1, 0. And it still goes through the point b, 1. But the b this time is between 0 and 1, so it's actually somewhere in here. And of course, since it's a decreasing logarithmic graph, that point is going to be higher than the point at 1, 0 because the b is less than 1 and the 1 is bigger than the 0. All right, let's use these properties to answer examples 11 and 12. Example 11, sketch the graph of y equals log base 5 of x and find the domain. So the first thing is identify the base. The base is equal to 5. Determine if that's the increasing or the decreasing log function. Since b is greater than 1, it is the increasing function. And then just graph the increasing log function. We know it goes through the point 1, 0 then somewhere over here, this is 5, 1. The domain is 0 to infinity, open at 0. You can put in the dashed line here if you'd like. Let's look at example 12. Sketch y is equal to log base 3 of x plus 4 and find the domain. So here we have x plus 4 inside of the logarithm. That tells me we're going to have a horizontal shift of 4 to the left. So first, let me make a short sketch of the log base 3 graph. That would be the increasing graph that goes through 1, 0 and 3, 1. Put your phones away. Please put your phone away. Thank you. Now, we're going to shift it over 4 units to the left. So we're going to start with the vertical asymptote that should be here at the the y-axis. We're going to go over 4 units to the left. So there's the new vertical asymptote. The point 1, 0 shifted over to -3, 0, because if you're moving 4 units to the left, you subtract 4 from the x-coordinate. And the point 3, 1, you're going to subtract 4 from that, and you're going to end up with -1, 1. Then draw the increasing log curve that goes through that. The domain for this shifted graph is -4 to infinity. Open at -4. You can tell where the domain should be because of where the vertical asymptote is. Okay, let's go ahead and look at page 5, applications of logarithms. So they use logarithms in a lot of scientific work. Among the scientific principles that they use logs for, these include finding the acidity of a substance. That uses the pH scale. Finding the wave energy from an earthquake, the loudness of sound, and the intensity of light. Let's look at one of these examples with the pH. The pH scale is used to indicate the acidity or alkalinity of a liquid. In particular, pH is equal to the negative common log of the concentration of hydrogen. Okay, so the symbol bracket H plus bracket, that is the concentration of the hydrogen ions in a liquid. So you may remember this from chemistry. H plus is the hydrogen ion. And then if you put brackets around something like that, you're asking for the concentration in moles per liter or some other units. Now they baseline this with a pH of 7, that's water. Okay. If the pH is less than 7, then the liquid is acidic. If the pH is greater than 7, then the liquid is basic, or also called an alkaline. Find the pH of vinegar and bleach, which is acidic and which is basic. So the formula for pH, and by the way, they use this for other things as well. You can also find POH, right? The OH ion. You can do that. But here, most of the time, they just use the hydrogen ion. So pH is negative common log of the concentration of hydrogen. So for vinegar, by the way, do you know which of these is acidic and which of these is basic? Just from common knowledge? Is vinegar an acid or a base? It's an acid, yeah. Let's find out how bad it is. So the lower the pH number, the more acidic something is. The further away from 7 it is. The higher, above 7, and further away it is, the more basic it is. So for vinegar, the pH would be negative common log of 5.0 times 10 to the negative third. And let me go ahead and tell you the answer. Then I will show you how to do it on your calculator in a moment. So that is 2.3. So since that's less than 7, that's an acid. And then for bleach, the pH is equal to negative common log of 2.0 times 10 to the negative 13. And if you work that out, you get 12.70. So that means it's basic.